So we are trying to do an optimization, and for that purpose, actually, we are trying to find, let's say, a version of the design which has the minimum compliance, which is the inverse of stiffness. So we can say that we are trying to find a hard or stiff part, which can be also considered as the design which has the minimum compliance. So it's not soft, it's stiff. And at the beginning of this optimization problem, we have some amount of material, and we want to distribute this material properly into the design domain so that its performance will be maximized. And this is, as you see, weird kind of actually design domain. This whole part is a design domain. We have boundary conditions, we have traction forces, distributed forces, body forces, and we have some regions, these gray regions can be modified. So this is actually the design domain. So any point, any kind of element is considered as a design point or element. But we cannot do modifications on this white and black regions, since in the white region we don't want to have any material, but in the black region you want to have material, and they are not in this design problem, not the part of design problem. And we are trying to adjust the stiffness of all these elements, since if you remember we were dividing this design domain into some elements to make it easier. We will have a stiffness tensor for each item in our design domain. And during this actually optimization, we are using the energy equations, and we will try to do the optimization by using some different energy forms. And the first one is bilinear form. As you see, the integral over the whole domain. We have the deflection of each point, their displacements, their stiffnesses, again important. If you do this multiplication over the domain, you can obtain the overall energy of the part. We have the strains, and we have the load on the part. Actually, it composed of body forces and traction forces. And we can actually represent the same problem in various forms. And after a few slides, you will see that we try to find a way which is actually much easier in terms of computations. This is another form, for instance, the minimum compliance form, or we can say that we are trying to maximize the global stiffness. And so we are trying to minimize the compliance, but the thing is that this should be satisfied. The relation between the forces and displacements should always be satisfied. And the thing is that your stiffness should always be among the possible stiffness values. So we are doing a kind of discretization over the domain. We have two fields, displacement and stiffness fields, and for both of them, we are using the same mesh. And this is, as you see, another representation. This is in matrix form. We are again trying to minimize the compliance. This is our force relation. This is stiffness times displacement should be equal to the total force. And this should always be satisfied. At any point of your optimization, this should be valid. And this is about the summation of all the stiffness values. For instance, let me show you one of it. Let's say this is K2. Then it will be a kind of a matrix, and we will have a specific value. Let's say 10. I'm just making up this value, and if you sum all these up to n, then you will obtain the final or the overall stiffness tensor. That will be our overall stiffness K value, and it will be composed of various values. And we will be performing the analysis, finite element analysis, using these stiffness values. And in this optimization, we are always assuming that into these elements, we are adding kind of isotropic materials. Their properties are the same. So once you add a material into a specific element or add another material to an element which is far away, they should have the same properties. And you cannot have, let's say, 50% of the cell is filled with material. It's not possible in this optimization, but if you do some modifications in the equations, and if you also capable of actually fabricating such intermediate densities, then you may go with such an approach. And at the end of this optimization, we want to have a kind of a binary image. So these elements might be filled with material or they may be void. So these are the things, yes. Focus on a specific element. This is one element, and it may have material or no material. This is how we represent it. Actually, this is the property of an isotropic material. And if you have material in that element, then you are simply multiplying this value with 1. And if you don't, you are multiplying it with 0. But this is a kind of a discrete approach, right? Whether you have 1 or 0. But in order to make a smooth, let's say, optimization, we will replace this part with a kind of an function, density function, and that will be our design variable. Since we are trying to adjust this variable so that the part will be optimized. And obviously, the summation of all the materials in each cell should be less than the given volume. This is the volume of material, the whole volume of the materials. We are taking interior of the whole domain, and obviously it should be less than the available of material. Any questions, guys, up to now? So now we have a kind of a discrete design problem. But as I said, in order to make things smoother, we need to have a kind of continuous variable. And if you have a continuous variable, then you make do your optimization by doing penalties, by applying some kind of penalization at some points of your iterations. And for that purpose, we make use of the density. Density will be our variable, our design variable. And at the end of the optimization, we will tell the user that this element will have such amount of density and the other one will have 0, the rest will have 1. So we will be deciding on the densities of the element. This is our main aim in this optimization problem. Yes, this is things I discussed. We don't want to have intermediate density values. That's why we'll be using a penalization. And the method we are going to follow is called as solid isotropic material with penalization, which means that for each element, we are using the same type of material. It has isotropic properties, and we are trying to set the density with the help of this penalization. Now we will see how we are going to do this penalization. So as I said, instead of using 1/1 sigma mat variable here, this time we have a continuous variable in this equation. And this is the density rho of x to the power p. And here it says that power should be greater than 1. And again, we have the same volume constraint. This is integral over the whole domain. If you multiply the density with the volume, then you should get the whole volume. And the densities of any element is always in between 0 and 1. It cannot be greater than 1, obviously. Yes, so the density will be actually interpolating in between 0 to e to the power of 0, which is actually our main or the material properties of a given isotropic material. So for instance, if your density is around 0.001, and if you take P as 3, let's say, then it will be very low, since it's actually 1 to the 10 minus 3 initially, and if you take the power as 3, then it will be very low, almost equal to 0. So in minimum, it will be equal to 0, but in maximum, it will be equal to this value. And there's a question about ij, k, and l. It's about the tensor. This is tensor, stiffness tensor is describing the location of your elements and the directions of these, let's say, stiffnesses. While choosing P, we prefer to have it actually larger than P1, since we don't want to have intermediate values, intermediate density values at the end of the optimization. Either we want to have 0 or 1, and it's possible with P is greater than 1, and mostly we prefer to use P is equal to as 3. And this is a kind of an explicit penalization, not an explicit penalization, since we are not defining the penalization, let's say, algorithms or penalization rules. Instead, we have a continuous function, continuous design variable, and with the help of this power, we are doing kind of an penalization, and this is an implicit penalization. And if you have an intermediate density values, and if you want to intentionally actually have such intermediate density values, then it's better you find a special material which you can set the density of it. Otherwise, it's not possible with conventional manufacturing technologies. You cannot manufacture and design which has, let's say, intermediate densities, let's say 0.5, 0.6 at a specific point, and it has, let's say, 0.9 density at another element. This is not possible, so that's why we are focusing on a binary type of result. And if you actually satisfy these equations, these inequalities for the power P, then we can say that it's realizable. We can manufacture such 2D or 3D parts. And what is in 2D? We are trying to have a relation between the power and the Poisson ratio. So if you satisfy this one, then that means it's fine. You can manufacture the topology optimized design. And for 3D, we have another one, as you see. And for most of the case, it's better you take P as 3 in 2D, and for 3D, it's possible to take P as 2, but again, you can simply take it greater than 3. Any questions, guys? So now we are trying to change these formulations to make it easier for our computer problem, so that we can solve it on any kind of programming language or any kind of software. And we will be using the potential energy, and over this equation, we will have a better and easier formulation. And this is our function, the displacement field U, which is here in this equation, force equation, and we are trying to find the minimum of this value, which is directly affecting the potential energy. So at the equilibrium, where your actually part is just staying, then the potential energy should satisfy this inequality, and then we can write this design problem again in such a way: minimum displacement and maximum admissible stiffness, or we can have another formulation in terms of stresses this time. This is compliance. If you remember, is compliance, and these are our stress values, and we are trying to minimize stress with the help of minimum stiffness vectors. This is our compliance tensor, as I mentioned. We are trying to minimize the stresses, and they will be, actually, they should be a member of admissible stress fields. This is the equation. And once you actually know the displacement field and the optimal structure, then you can try to distribute the material such that your strain energy is maximized. And now we will go into the details how we're going to solve this problem, since we need to have some specific algorithms at different parts of the problem, overall design problem. And the overall design problem will be solved with SIP, but at intermediate steps, we need to use other algorithms. These are not that important. It says that you need to update the parameters so that the optimization will be done in a shorter time. And the first thing we need to consider is the conditions of optimality. You need to satisfy this actually at any steps. Otherwise, you cannot go on with the upcoming, let's say, iteration. So this is actually a nice property. We have the flexibility of actually updating each element independently, and this update will not be affecting the other points. But the thing is that we need to have some kind of a connection between the elements. If you lose that connection, then it will not be possible to have proper designs at the end of the optimization. And that's why actually at some point after this conditions of the optimality, we have a sensitivity analysis and filtering options so that you always have continuous, let's say, truss-like structures and design. So now this is our for final formulation. We are trying to minimize the compliance, and we have the overall force relation, force and displacement relations. And this is our design variable. It should be satisfying this equation. For each element should satisfy this equation. We have the volume constraint, and this is the density constraint. And in between iterations, we need to actually redistribute the available material. Let's say you have 50% of the initial volume. So assume that you have a part which is composed of 100 elements. And at the beginning of the problem, it says that you only have 50 units of material. So what you're going to do, you need to distribute this 50 units of material properly and have connections between each item, and your design should be as good as possible. And in between these iterations, we need to distribute it with the help of these equations. This is Lagrange multipliers. As you see, this is the density of the cell in the next iteration. This is density k plus 1. K is actually the current density value, and k plus 1 is the next density value. And we are trying to calculate these values, and then depending on this conditions, we select one of the options. For instance, if this is satisfied, then maximum of these two values should be assigned. Or if the second condition is satisfied, then minimum of these two values should be assigned. Or lastly, if any of these are not satisfied, then the density should be equal to this value. And Bk is here, as you see, and this lambda is Lagrange multiplier. And we have some parameters, eta, zeta. So these are kind of optimization parameters, and you need to set them at the beginning of your problem. So in this update scheme, actually, as I said, with the help of these equations, inequalities, we are redistributing the material. And we have a tuning parameter eta and move limits zeta. And as I said, you need to adjust these values depending on your part. These are the same issues. So at the beginning of the problem, there will be a huge change between the volumes, between the consecutive volumes. But once you are actually approaching to the final design, then there will be less change in the volume. And the value of this language multiplier can be determined by using a specific algorithm, bisection method or Newton method. So that should be actually the part of our optimization. We need to use some special codes for that. Yes, these are the same issues we said. At some point, actually, we will have many variables. In order to overcome this issue, we need to use a mathematical program. It's a method, a popular method. And again, we will directly use as kind of an available method and use it in our overall algorithm. These are okay. Any questions, guys? Up to now? So what we are going to do in this optimization? At first, we need to do some pre-processing of the geometry. We will define the boundaries of the geometry, the non-material regions, fixed material regions should all be defined, and also the loads applied on the geometry, the boundary conditions should all be defined in this first step. And then you're going to do the optimization by using the fundamentals of SIMP, and later, if it's required, you can do some post-processing on the results of this optimization step. So let's focus on briefly on the pre-processing part of this implementation. Assume that this is our design domain. We need to define the boundary conditions, the loads, and if you have fixed void regions, fixed solid regions, they all should be defined in this first part. And then after they're all defined, you need to construct a finite element mesh. It should be fine enough to give you a reasonable result. And the thing is that the given mesh, this obtained mesh at the beginning of the problem is not allowed to be modified actually during the optimization, so it will be always fixed. And you need to have some data structures prepared for finite element analysis, displacement, and other density fields. And in the optimization, this is the second step, the optimization. We will be using obviously these finite elements. And after each design, let's say offer, we are going to do a finite element analysis and determine the amount of our compliance. You'll check the compliance. If you are not satisfied, if there is a huge difference between the previous compliance value and the current value, then we should continue. But if you realize that there is not much change between the previous compliance and the current compliance, then you can stop and say that this is the optimized design. And at the beginning, we are distributing the material in a homogeneous way so that each element will have the same amount of material. And then we will perform optimizations at each iteration. As I said, check their compliances. If you're not satisfied, then you can continue, but if you're satisfied, then you should stop. And obviously, this language multiplier is an important issue since it's the main, let's say, main part of the optimization where you redistribute the material over the design domain. Yes, these are, yes. The third step is post-processing. And if you're not satisfied with the binary image with the pixels, you may have kind of smoother lines over the domain so that it may be easier to fabricate, but it's not a must. It's up to you, up to your application. You may do such further modifications on the result of the optimization. Any questions, guys? Now I will show you actually the Python code. you have questions, you can ask, but I will be using my other computer. Yes, this one. I think now you see the Python code. This is available, by the way, on top of .dtu, I think something like that. If you just search for it, you can easily find this code, or I can send you a link if you're interested. It's a very short, actually, Python code. As you see, it has just 165 lines, and it is developed by these guys in January 2013. So let's focus on to these parts one by one. So let's have a look at the import part. They only make use of simple libraries like MP, matrix, some kind of solving libraries, and lastly, a plotting library. We close this part and have a look at the main function. And here you see the inputs to this optimization function. They have the number of elements in X. This is for finite elements, element mesh creation, number of elements in Y, the volume fraction is the amount of actually material you want to have in this design. And then we have penalization, the penalization factor, and our mean IT size, it should be about the sensitivity analysis we will discuss in a moment. And this FT, I think, is again about sensitivity and density. The filter method actually changes with respect to this PT value, as you see here. If it is 0, I think it should be a sensitivity-based optimization. If it's 1, then it will be density-based optimization. Then they have some values, as you see here, E min, which is actually, it should be 0, but they don't exactly use 0 in order to not have some numeric problems. They are using a very small number, but the maximum value will be 1, which refers to the isotropic value, the value of the isotropic material. And then they are doing some calculations here, computing the amount of material they have, and doing some meshing as far as remember. This should be, yes, building the index vectors for the compliance matrix formats. This is done here. Then constructing the index pointers for the, again, the same approach. These are all for actually finite element analysis, since they need to do a 2D analysis, and for that purpose, they create such matrices, and this loop is for that, actually doing some multiplication between the elements, and then doing the assembly here, and outputting the, I think, the result in a different format. Here you can see they are setting the load, initial conditions, the support boundary conditions, they're all set here. Since, for instance, if you have fixed support, then the displacement of the elements actually connecting to this fixed support should always be equal to 0. This is done here. And then they have a loop for the optimization. Yes. This is the main optimization part. Here they are doing the optimization. Let's discuss the details of it. As you see, they have a change variable. If the change is greater than 0.01, then they continue with the optimization. But if the change is less than that, then they stop and tell that this is the final design. And another constraint they have, that they don't want to have iterations more than 2000. So this is for setting up and solving the finite element problem. These are for that. And then they are removing constraint degree of freedoms from their matrix, solving it. as you see, U is equal to K and F. So they are actually solving to find displacements. Displacements are represented with the vector U. And here, the main optimization is carried out. The objective function is checked and sensitive analysis are performed, filtering. And lastly, they are filtering the design variable, the density variables, computing the change between the previous one and the current one, and then simply plotting it on screen. Let me minimize this one. They have another function. I think this is about, again, element stiffness matrix. They use it in the finite element analysis. This is for optimality criterion. Checking some, we will discuss that they have moving method of asymptotes. Optimality criterion is an important issue. They do it here. And in the last part, they provide the variables and try to come up with an optimized design for the cantilever beam. By the way, this is for a cantilever beam, but there are also different versions. Let me show you some results. For instance, assume that this is too much. I want to decrease it to 90 and let's make it 30. The number of elements in X, number of elements in Y, and we have volume fraction 0.4, but let's make it 0.5. These are, as I said, a parameter for sensitive analysis, and the penalization is right now 3. And ft is equal to 1, then that means it's a density-based optimization. Now let me save and run this optimization. I'm not sure what you don't see. Okay, let me stop and share my whole screen. Yes, now you see optimization is being carried out. Here you can see the number of iterations, the change. And once the change is not much, it will stop. But right now we have I think an error. What is the error? Or I think it's due to my actually inputs in the keyboard. Let me run it once again. So you can see how this part is actually being modified. After each iteration, the number of gray regions is being decreased, but at some point, we will not have much change between the consecutive designs. So again, it failed. I think I should check some details maybe. And I want to show you the effect of penalization. Let's make it, for instance, 1. You see, we don't actually have truss-like structure. We have more gray regions. Any questions, guys? Do you have? Let's don't change the elements and make this one 1 again. Any questions?
Teacher, in general, we are just giving the penalty numbers in the beginning, right?
Yep. And we don't change it during the iterations. It's always fixed.
Hocam, is this code only valid for cantilever beam, right?
This one, yes, but you can modify it for any type of beams. So what you need to do is actually, let me show this one here. You need to modify the boundary conditions. Where were they? Yes, if you modify the boundary conditions and the load here, then you can have another optimization on a different beam. But this code is for just 2D shapes. If you want to do it on 3D shapes, then it's more complicated. You need to have a much powerful computer. But for 2D shapes, simple shapes, in less than a minute, you can obtain the result. Any questions, guys? Let's go back to the slides. So we were discussing these issues. We said that we should use any the same finite element mesh, and we can define any kind of boundary conditions. We have flexibilities in terms of these, and we can also define non-designing parts, fixed regions, void regions. They are all possible in this method. You can always define such regions, and then your algorithm will actually give you such results, having fixed regions or having no material regions. So this is a summary of actually the flow chart of the overall design approach, topology optimization approach. This is the initialization. Initially, you need to do a kind of a guess, distribute the materials in a homogeneous way, and then do a finite element analysis. Since you have a load, you have boundary conditions, fixed support, moving support, you do the analysis and determine the compliance of your design. And then you need to redistribute the material with the help of these operations. These three are actually the main part of the, let's say, computation. You then sense analysis, do low pass filtering, and later optimize, distribute the material. And depending on the result of it, you update the density of each finite element. You see here. And then if you have not converged yet, then you need to do these steps once again, and you will be done once you have less difference between the previous and the current iteration. And lastly, you can do kind of an post-processing, as you see, instead of having such an binary image or such pixels, you can modify your design and have smooth edges. And as we have seen in the Python code, the programming complexity is not much. If you make use of proper, let's say, finite element method codes and some optimality criterion or moving asymptote codes available, then things will be much easier. They also have a MATLAB code for that. And in 99, I think the current version is 88 lines. In 88 lines, they can do this optimization. Now let me show you their website. Any questions, guys? Oops. Let me share it with you. Yes, this is the website of their algorithm from ODTÜ. And here in apps and software, you can download 3D versions, 2D versions for your iPad or for your tablets. Even they have an let's say library for Grasshopper. It's just in 2D, and they have these MATLAB codes and Python codes here. You see now they have the optimized 88 line of codes. Even I think they decrease it to 71, but they need to use conv2 function. Let's have a look at the MATLAB function. I haven't installed MATLAB, but at least I can show you the fundamentals. Yes, this is a MATLAB code. But again, the same. They are preparing the finite element analysis, some matrices to make the actually computation faster. And then here they are defining the loads and the supports. By the way, half beam is actually the cantilever beam. And filter is prepared here. And initial iteration, material is distributed, and this part is actually the main optimization, this part. As you see, again, they are checking the difference with between the previous and current designs. And in this optimization, finite element analysis is performed, objective function is checked, the sensitive analysis is performed. On the sensitive analysis, you need to have filtering so that the elements will be connected together. And by using the optimality criteria, they update the design variable, which was our densities. This is done here. And lastly, they print these results on a plot and do some coloring. So once again, go back to our PowerPoint. Any questions? So you can say that they are now working on a rectangular design domain. They are performing fourth order interpolation for displacements. And they are working on the densities in an element-wise manner. They perform finite element analysis and plotting in just 99 or even less number of lines in MATLAB. So what do we do in sensitive analysis? Actually, we have a design variable and we need to consider the changes in this design variable. And if you have, let's say, too much change, then you should be careful about it. The connection between the elements is, again, an important issue. And we do it with the help of the sensitive analysis. And for that purpose, since we have many variables and some constraints, we make use of mathematical programming for that. And the algorithm used in the approach is method of moving asymptotes. I'm not going to discuss the details of it, but it's useful once you have many variables and some number of constraints. This is our formulation again, and we perform the analysis on this equations. As I said, we'll be checking the connections, and we obtain the derivatives and sensitive analysis always performed on the derivative of the goal function, objective function, and we obtain it by simply using the chain rule. And another thing is that at any point of your iteration, you should always satisfy the simple equation. K times U should be equal to the total force you have on your design. It should be always satisfied. Now, if you look at the general steps, again, these are the same things, but in the method of moving asymptotes, we are making initial design and then doing, again, the finite element analysis and checking the compliance of the design, distributing the material, and checking whether you have huge changes or small change between the consecutive designs. So these are the same things we discussed. And depending on the computing platform you are using, there might be little difference, but the fundamental approach is like this. This is a summary of the MATLAB. And now let's briefly talk about some specific issues on this optimization. As we have seen, meshes are quite important. It determines the amount of time you are spending on optimization, and also the results will be affected by the size of these meshes. So it's better you find a proper size in which you will be spending less time for computation and have good results. Since we want to have finer structures. And in order not to have gray regions or composite materials, we prefer to have P greater than 3. Otherwise, as we have seen in the Python implementation, we may have gray regions, and that will be quite difficult to fabricate. And some methods is quite difficult, but you may try to increase this P. And as you see in this code, we don't have such an option, but you may try. There are some studies performing such an operation on the power P that are slowly raising this P so that the computation will be taking less time. These are the same issues. I don't want to repeat them once again. Yes, why are we actually focusing on topology optimization? Since these days we can use it as a design tool. You don't need to design the details of a given part. You can simply set the boundary conditions, fixed design regions or no material regions, support conditions, other things, and then this approach will give you a proper design which uses less material but performing better compared to your conventional design approach. And obviously in this optimization, physics is already included, so you don't need to further do some finite element analysis or some other analysis to check whether your part is functioning properly. This is already done in this topology optimization, so it will save you lots of time. And obviously you may not be satisfied with the output, but you can do some modifications post-processing and at least get a better result with the help of the same software. Here are some examples. For instance, if you use coarser meshes, that will be the result, but if you use finer meshes, this is another result. Here you see an example. We have such laws, and instead of using material at the center, it is removed, as you see. These are another example. So I think this is for a telescope. We have many parts, and the problem is how to connect them, and this is done with the help of, again, optimization. Sorry guys, once again, it's always ringing when I'm teaching. Here you see the mesh refinement, the effect of actually number of meshes. In the last case, in case C, we have, this is the typo, we have 17,200 number of meshes, but in the first one, we have much less than that, and you can see we have less number of lines, trusses, but we should have the same amount of material. And obviously, this is quite difficult to actually fabricate. It depends on the size of it, but I would prefer this one in terms of fabrication. Another example for the cantilever beam, as we increase number of meshes, you see this is B, we have about 300, then 600, 4,000, and at the end we have 19,000. And you can see that it's highly smooth and still, but we have some gray regions which are close to the black regions, and it's not a problem since they are close to the black regions, so you can easily fabricate them and you will not have any problems in terms of manufacturing.